So this, these slides that you are seeing are, and that is why the date on it is incorrect, are for my Caroline Herschel talk that I gave at the Royal Astronomical Society down in London a couple of months ago. I am going to base this presentation on these slides, but also jump back and forth between other windows that I've got open, because there's a lot of cool stuff that's happened in the sky survey world recently that we can talk about. And I'm going to skip on some of the more, low to the ground presentation stuff, because you understand more about the universe than the average Joe. So I'm now a researcher at the University of Oxford, partnered with Queen's University Belfast and Sheffield University. And my job is to find big explosions in the sky using sky surveys. And I specifically design AI systems. I hate the word AI, and we'll see that very soon. But basically, I design automated systems to find these explosions. So my bread and butter is things that go boom, but you can find other things with these telescopes. So the start of this, and by the way, the Caroline Herschel talk as it is, I'm not going to give today because it's too long, but you can see it online. It was recorded in Bath back in November. So we're just going to go through the slides a little bit differently. So the way I start the Caroline Herschel talk is by going back in time and how astronomy started making more and more discoveries as we gained more and more technology. So the first pillar of Western astronomy is obviously, why does this not work? The telescope. So we started getting telescopes in the 1600s. People were initially pointing them out into the horizon to see other boats. But then Galileo was like, what if I pointed up? And found some really cool things like the moons of Jupiter. Other bits of cool tech that helped astronomers was the invention of photography in the late 19th century. That really brought astronomy into the Industrial Revolution. Photographic plates allowed us to start making proper sky surveys. Instead of just recording things by hand in notebooks, people could take a picture of the sky and map it that way. Then things accelerated massively in the 20th century. Semiconductors were invented in the 50s and made better in the 60s and 70s. That's what made computers go from things that fit into a big room to things that fit on a lap. And that also allowed us to invent CCDs, things that we use for imaging that you probably have in your telescopes. Although you might not have CCDs, you might have other kind of systems nowadays. The late 20th century also brought us rockets that we can launch into space. And obviously, space is nice because it doesn't have the atmosphere. We can take some beautiful pictures like the Hubble Deep Field. I'm sure you've seen that picture many, many times. Although one interesting thing about that specific zoom in, crop out version that I've got is that this is nearly precisely 100 times smaller than the moon, that shot of the sky. And there's still hundreds and hundreds of galaxies in there. That's the modern version of the deep field. That's JWST. You can recognize the JWST pictures by there, and I'm going to use my mouse, by their 6 pronged spokes. And you can see some really cool galaxies distorted by gravity there in the background. So cool stuff happens when you get new technology, and discovery in astronomy, like in other sciences, is a partnership between people and tech. And that's the theme that I explore in this presentation, especially in and exactly the kind of technologies that help us and that don't. I'm going to be a lot less heavy on the tech today and a lot heavier on the astronomy, but you're welcome to ask me questions later on. So then blah, 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 make it personable with pictures of me. That's the NTT, that's the New Technology Telescope in Chile. I was there in June last year. We didn't observe because things were not so great. You can see the clouds there. Actually, the clouds were not the problem. The clouds were blown away very quickly by very, very strong winds. So I got the opportunity to take beautiful pictures with my phone, because when the winds are too powerful at Lucia, you can't open the dome because then the telescope breaks. So this is taken with my phone and the phone that I have right there, which is nice. There's a couple of filters on it, but it is mostly just a 5-minute exposure that gives it this depth. There's a better picture with ESO. You know that there's billions of stars in the universe. Well, billions of sources in Atlas, specifically the sky survey that I study. Now, a little bit of audience participation, and hopefully the people on Zoom can still hear me. How many, order of magnitude, how many stars can you see in the night sky if you're in a dark sky reserve?
10 to the 9.
10 to the 9. You can see as many stars as Atlas, not us with the telescope, us with our eyes.
Oh,
Order of magnitude, you're perfectly right. Order of magnitude, thousands. And so the usual analogy that I give people, because they're not astronomers, people that come to see my talks, is this presentation is usually like an hour long, so it's 3.6 thousand seconds. 1 billion seconds is 31.5 years. So I'm just over 1 billion seconds long. So this is the kind of order of magnitude between what our eyes can do and what the telescopes that we use can do. So the sky is big. We've got cool things happening in the night sky. It's not just big, it changes. We've got Betelgeuse. By the way, the reason that Betelgeuse is the wrong way around is because I used to live in New Zealand. And that's what Orion looks like in New Zealand. Its head is upside down. It was the great dimming event of 2019. I don't know if anyone got the chance to observe it back when that happened. We've got comets and asteroids. This is not really an asteroid. I'm cheating a little bit. There's a moonlet of an asteroid that was impacted by the DART mission. And this ejector was actually captured by Atlas as it was happening, which is quite cool. So loads of things changed in the night sky, and the things that I care the most about are the things that happen really, really far away. So not necessarily the variable stars like Betelgeuse or the comets, but it's dying stars like supernovae, kilonovae is neutron stars merging, tidal disruption events is black holes getting biggish and eating a star, and then other things like active nuclei. Now, this slide is very busy. The point of the slide is not to tell you about all of these things because we don't have time for this, but it's just to highlight the timescales I've written there. So those timescales are the sort of timescales on which these events look different, significantly different enough that you want to take a new picture so that you can learn something new about them. So supernovae, every few days, they will look really quite a bit different. If it's really early on, it could be even every few hours. Kilonovae, you've got hours. You've got hours in a couple of days, maybe. Tidal disruption event, maybe a few weeks. The point is, things move really, really quickly on in the world of transit astronomy compared to the timescales that we are used to in astronomy. So you have to survey the sky not only across its spatial extent, but also across time. If you want to understand how these things explode and create the elements that we're made of, you have to survey the sky over and over and over and over again. And that's the kind of capability we've only had in the last 20, 25 years. That's a really 21st century technology that's allowed us to do that. And what's allowed us to do that is dedicated sky surveys, whose job it is to survey the sky over and over and over again. So we've got a bunch of examples here. I'm not going to cover all of them. Some of them are defunct. Some of them are about to be defunct, and some of them are very current. So Atlas, that's the team that I'm a part of. By the way, the scale is obviously not right on the sky, but it is correct with respect to the moon and with respect to Andromeda. So the field of view of one Atlas unit is about 29 square degrees. And we've got 4 of these scattered across the globe. I'll show you a map in a second. There's also the Little Transient Factory here. They only have one site in the US. There's Go2, which is a little bit bigger than us. And they've got 4 sites as well. Well, 2 sites. They've got 2 telescopes in Palma, 2 telescopes in Australia. And these things can survey the sky with a cadence of, for Atlas, it's 1 to 2 days. For ZTF, it's a little bit more. And for Go2, it's a bit different because their strategy is a little bit different, but of ordered days. So we're getting there in terms of how we can map the sky over and over and over again. So Atlas is the one that I'm going to focus on because that's the one I'm a part of. The main point of Atlas is to find solar system objects. So it's the Asteroid Terrestrial-impact Last Alert System. That's why it's funded by NASA. Still is. Although the NSF cuts are getting really, really scary. But we still have the money. And its principal mission is to do terrestrial defense. So it could find something that comes too close to Earth, whether we can do anything about it. I don't know if you've seen the movie Don't Look Up. No, I recommend it. It's very funny and very depressing. So Atlas has 4 units across the world. We've got 2 in Hawaii. Those were the initial 2 units. And we also have 1 in Chile and now 1 in South Africa. There's another one that's just started to work that's in the Palm. It's hidden by this logo. It's working. We're starting to ingest data. It is on Skype, but there's a little bit of work to do to clean the data up. Now, because we have these 4 units scattered in the north and the southern hemisphere, we have nearly a 360 view of the sky, which is what we want if we want to map it very well. But obviously, the 360 view is not enough. We also need to have the cadence. Now, I've added a couple of slides because I thought I've got some nerds in the room. I'm going to tell you what the telescopes actually are. I don't usually tell people what the telescopes actually are because they don't care. So our telescopes are actually quite small. They're only 50 centimeters, the primary mirrors. And we've got some, so the original kits were custom made by a guy that has now retired. That's why the Palmer unit is taking a little while longer to work because it is off the shelf and we're figuring this out. But the original units are just a right-shifted telescope with the German mount, with the big counterweight on this side, in a pretty rudimentary dome. Really fast focal ratio because we need the big field of view in order to get the cadence that we need, which is of order 24 to 48 hours. The filters that we have are, it's the next slide. So I'll tell you the filters and then the strategy. So the filters are a little bit different from the classic Johnson, Cousin, UV, RI, or the GRI of SDSS. We've got these very broadband cyan and orange filters because we don't have a big telescope, so we need to capture as much light as we can. And we mostly use the orange filter because that's where a lot of our stuff is brightest and because we get a lot less issues with the sky. The sky is really bright in the blue. And so especially when the moon is high, the cyan is basically useless. So we put the cyan in a few days during the moon cycle when it is new. So the strategy of Atlas is focused on its primary mission, which is finding and tracking asteroids. So the observation strategy is 4 observations separated by roughly 15 minutes. Each observation is 30 seconds. So you take a snapshot, and then you go to another patch, another patch, another patch, and then you go back every 15 minutes, and then you move on to the other patch of sky, unless there's something specific you're trying to track. And with this strategy, we get magnitude limits of order 20. So 19.5 things look okay, 20 things really are in the weeds. If we stack our shots, we can get to below 20. But it can be really tricky there. We saturate around 12.5 mag, so there's a lot of really interesting things that we just can't see. We have a mask on it because it just fries. Well, it doesn't fry the detector, but it's completely saturated, so we can't use the data. Okay, that's just the moon. Cool, so we have this really large field of view, incorrect numbers, but that's okay, doesn't matter. And here you can see a slightly overwhelming dashboard that we have for one of our units. Actually, I think I have a live one, but I don't know if, well, South Africa, is it night in South Africa? Nope. No, that's Chile anyway. I'm not looking at the right one. I was really hoping that maybe I'd have a cool one to show you. No data. Oh, yeah, we're taking pictures. 8 minutes ago. Here is a live dashboard of Atlas, so you can see the the bits of the sky it's already done, different transparencies because there's different patches that have been done once or more than once. And here you can see the recent images. So things are going pretty well. No massive issues, you know, a little bit of bleeding from the bright stars, but just completely normal. So things are going well. That's nice. So that's Atlas. And Atlas is really good at finding asteroids and things that move. Proof of that, it found the third interstellar asteroid that's, or is it a comet? I think it's a comet. I've been on holiday, guys. I'm sorry, not kept up. But it found the third interstellar object that we've ever found in the solar system. It was found very recently. And it's still being observed by pretty much everyone that's got a telescope that can point at that thing. So that they can determine the orbit and then figure out exactly what it's made of. But I have no big news on that because I've not really kept up with it. So it can find movers very well, but it can also find things that go bang, which is what I'm interested in. And the reason I'm interested in things that go bang is because they can tell us about where we come from in the universe. Now, the first type of thing that go bang that I'm going to talk about today is the supernova, the one that everyone knows about. At least I think so. Has everyone heard of a supernova? Yeah, okay. I'm preaching to the choir here. Supernovae I call. For all intents and purposes, there's only two kinds tonight. The low mass and the high mass. Supernovae were first discovered about 100 years ago, less than that. And then astronomers have spent the last 90 years creating subcategories of subcategories of subcategories, not necessarily useful for what we need to talk about. For all intents and purposes, there's only two kinds, the low mass stars and the high mass stars. The low mass stars, supernovae, come from white dwarfs. So those are the dead remnants of the most common stars in the universe, things like the sun. And they are important because they create most of the iron in the universe when they explode. But they're also very useful to help us keep track of the expansion of the universe because they're standardizable candles. Because white dwarfs have this property of exploding at a specific mass, you kind of know how bright they should be. And if you know how bright something should be and you know how bright it looks, you can determine the distance. The high mass star supernovae are my personal favorite, but I'm completely biased here. That's because that's the world that I come from. So by high mass star, I mean something that's born with more than 8 times the mass of the sun. And these things explode when they reach the end of their lives. So they run out of fuel in their core, the core collapses under its own weight, and then creates a neutron star, rebounds, explodes, creates most of the oxygen, calcium, and other intermediate mass elements that we've got in the universe. And like I said, it also makes a neutron star, which you can see here. By the way, none of the images I'm showing you tonight are AI generated. We live in a world where I have to say this. No AI generation in any of, okay, caveat, one of them, the one from my phone, but that's not my fault, that's Google. But this is a real image, which you may have seen already. That's the Crab Nebula. It's a stack of 5 different images from 5 different telescopes. And the beautiful purple one that looks like CGI is actually Chandra telescope observations. For Chandra's 30th anniversary, they observed the crab for what, 30,000 seconds, 30,000 kiloseconds, a crazy amount of time. And the crab is very, very bright in the X-rays. And you can see why, because it's got this beautiful, it's actually a pulsar, a pulsating neutron star, with this pinwheel nebula. You can see how it's rotating, and you can see even the jet they're coming out there. So yeah, that's the crab. I love the crab. Now on neutron star, this is an artist impression, not AI generated, but not real either. Our neutron stars can go on and have another little cataclysm of their own and explode as kilonovae. This happens because massive stars are rarely born alone. They're either born in a binary or in a tertiary system or something like this. They usually have a friend. And when both of these stars die, you can find yourself with two neutron stars orbiting each other. And as you know, maybe, There's a little thing called the fabric of space-time, which we can approximate as an actual piece of fabric. That's a 2D version of a 3D model. Now in the classic experiment where you've got a piece of fabric, I need to use the mouse because people are online. In the classic experiment where you've got your piece of fabric and you put a big like snooker ball or something on it, you've got that divot that it creates. But picture two snooker balls next to each other. Well, now the hole that's created is more peanut-shaped. And that's what happens when you have two neutron stars or two black holes next to each other, because they're really, really dense. And so if they are spinning, then they create ripples in the fabric of space-time. And now I need you all to pray for the video to actually work, because it's a really cool video. Actually, okay, we'll try the video. I can't promise that it's going to look good on Zoom, because very often the frame rate on Zoom is garbage. And I apologize if it doesn't look good. I'm going to show it. I'm going to try and show it as is to the people in the room after the talk, and then we'll share the link with people online. Okay. Hey, it's not great, but it's not terrible. You can sort of see the gravitational waves because of the effect that they have on the light in the background. Now, as you can see, the black hole and neutron stars are spinning faster and faster around each other and losing orbit until eventually they merge. Now, the energy from the orbit is taken away by the gravitational waves. That's why they merge. It's not, there's no free meal in the universe. If you're making waves, the energy has to come from somewhere. In this case, it comes from the orbit. Now this is an actual simulation, by the way. I mean, it is CGI and an artist impression, but it is based on actual simulation by the OSGraph people. So it is as physically realistic as you can get it. Simulation, let's try that simulation. Let's see how well that looks. So in this case, the point is not to see the gravitational waves themselves, but to see what happens to the neutron stars as they merge and the mess that they make. So here we'll see them come closer and closer together. And as they come really close, they get distorted. They like, as they're touching, they turn into that peanut shape and then just shred each other apart and create that big ejector, that big donut. And that ejector, that material, is the kilonova. That's what we see. So that material that's ejected is very neutron rich, and it's capable of making some of the heaviest elements that we know about in the universe, like platinum, gold, rare earth elements that we have in our phone. You need a high flux of neutrons to do that, and this is the place to do it. There may be other places because there's a lot fewer kilonovae than we thought there were, but that's why we still have a job. There is science to be done. Right, so the final type of explosion I'm going to talk about today is the tidal disruption events. Because, I had hungry black holes in the title of my talk, so I had to put those in. And they're a really interesting piece of physics that I'm also going to use a video to explain, a video that someone else made. So we've got a beautiful interstellar-like looking black hole there. And in the distance, we've got a star coming in hot, and that star is going to get a little too close to the black hole. This is an intermediate mass black hole, something around of order thousands of solar masses. And bam, it gets shredded. That star gets shredded. About half of, I'm going to pause it here, about half of its mass gets flung out into space. But as you can see, the black hole gets brighter. That bit there lights up. So it's not the black hole that gets bright, because black holes are black. But the material that gets accreted by the black hole, that gets eaten by the black hole, can't just fall in magically all at once. It doesn't work that way. The material kind of, like when you have water that goes down the drain in the sink, it spirals into the black hole, and there's a traffic jam. And just like traffic jams on Earth, when there's a traffic jam, things get heated, and when things get heated in space, you get light. So basically, the material gets really, really hot in that disk before it enters the black hole, and it's that disk that gets so hot that you can see it in the telescopes. Right, and so the reason that these are cool is because, well, they make black holes bright. Black holes are very difficult to study because you can't make them in the lab, and they're very hard to see. But because of these stars that fall into these black holes and that create these tidal disruption events, you can actually probe the mass and the spins of the black holes, because the light that you get from that stellar material falling into the black hole depends on how massive the black hole is and on how quickly it is spinning, because it changes the gravity around the black hole. So it allows us to probe black holes that we would never be able to probe. And you might be like, what if I don't care about black hole? And it's a very, very valid question. But these black holes have to come from somewhere. So if you've got black holes that are thousands of solar masses, what made them? Is it stars that were thousands of solar masses? Is there enough of those stars in the early universe to make that? I don't know. Do you need stars to die on their own and then coalesce? We're still figuring out where all the black holes come from. But black holes don't, except if you listen to some cosmologists, black holes don't happen in isolation. They have to come from somewhere. So you have to understand everything in the chain beforehand, what stars happened before the black holes in order to get them. Right, so just looking at these three types of explosions, we can learn a lot about the universe, the origin of chemical elements, the expansion of the universe, the physics of black holes and neutron stars. And that's all well and good, but the only way to actually learn about these things and study these events is to find them. So let's find them. So in our sky surveys, the way to find these new explosions is to essentially spot the difference with the universe. And I'm going to talk a little bit about the AI, and that's where I'm going to start skipping stuff, unless people have specific questions. So here you've got two pictures. They're two crop outs from essentially the same picture of that Milky Way that I took with my phone that I showed you earlier. Remember, I was in Chile, I took a picture with my phone, 5-minute exposure, it was beautiful. There's two versions of that picture. There is a RAW version and there is a JPEG. Now, it might be very difficult to see because we're on Zoom, so I will give you the answer. But the difference between the RAW and the JPEG is that the RAW is blurrier than the JPEG for some reason. You can see the individual pixels in the RAW image, but the JPEG looks like it has high resolution. Now, for people that know about JPEGs, you'll find that confusing because a JPEG is a lossy form of file compression. So how does my JPEG have more pixels than my not JPEG? And that's because my phone is not just a camera, it's a smartphone. It has a smart camera with magic maths that creates more pixels. And by magic maths, I mean generative AI. And I don't know exactly what's in it because I don't work at Google. I just have the phone and I can't tell what's in the black box. But from my expertise, oh, by the way, I should say, I didn't say this before, I do have some expertise in AI. My job is literally at the border between the two. I'm paid by the AI big wig people. So I'm a weird mutt of an astronomer between big tech and astronomy. So from what I know about generative AI, this is what's going on there. And we'll have another example later in the talk. Now, instead of the what is AI, blah blah blah, because we're 15 minutes before the end, we're going to skip all of this. You're welcome.
We're about 10 minutes late starting.
Yeah.
So just let it.
Yeah,
if you've got the time.
We can. I run quickly through the slides. There's some cool AI history in there, which is less astronomy, but maybe still interested to the nerds in the room. So AI is a great marketing term that has had several summers and several winters. So you may have heard of the term AI summer, which is where people working on artificial intelligence get a lot of money, and AI winter, where people that talk about artificial intelligence are laughed out because they look like fools. Now, artificial intelligence is the kind of word that's been around for decades and used in psychology, statistics, computer science, philosophy, so many different fields with so many different specific definitions. It is not useful. AI, when it is used in the way that it is used today, is only used to sell you shit. Okay, let's be clear. Artificial intelligence, the kind that we are using and that is useful in our daily life, is machine learning. Machine learning is a form of statistical learning. But statistics sounds a lot more boring than AI. So people use the word AI, but at the end of the day, we're just learning functions. That's what we do. We learn mathematical functions. Now, there's not going to be a single equation in this talk because I usually assume that the audience has, I don't want to assume my audience has any mathematical background. So we're going to use an analogy for the mathematical function. A mathematical function is a little bit like a DJ deck. Now, you don't need to know how a DJ deck works. I don't. But the concept is simple. You put music on one end, you turn a bunch of knobs and dials, you change the parameters, and then a different sound comes out. So you've got input, you change a bunch of stuff, a different answer comes out. Brilliant. The concept of statistical learning is you've lost the instructions. So you've got the input, you kind of know what's supposed to come out. Either you know exactly what sounds are supposed to come out, or you know what the effect is supposed to be, like you want people to do this or to bob their head. You've got some information about what's supposed to come out, and you know what's coming in, but you don't know how this works. So you're going to start turning the knobs and dials until the outputs start looking right. Now, this is very similar. I mean, this is fully ripped off of an XKCD that came out 9 years ago, which some of you may have seen already, where you've got two lads, one on a pile of linear algebra and the other one looking a little bit curious. So this is your machine learning system. At the time, artificial intelligence was still not a very popular word. Yep, you pull the data into this big pile of linear algebra and then collect the answers on the other side. What if the answers are wrong? You just stir the pile until they start looking right. And that's essentially the job. So I would posit that beyond the marketing that we see today, people are much more willing to use the word intelligence, artificial intelligence, if they see a computer do something that they didn't think a computer could learn. So it's less to do with what the computer can do and more to do with your expectations of what the computer can do. And the example that I want to put forward for this is computer vision. So computer vision is a form of machine learning. You need big neural networks. Whatever you hear neural networks, basically it's just a big mathematical function. It's just a way to make a big function. Convolutional is just filters. So computer vision was the stuff of science fiction for a long time, you know. You had a very futuristic looking building and an action hero walking up to a door and scanning their retina and the door opens magically. But today we take it for granted that Facebook can recognize your grandchildren in pictures, or that a camera on the highway can take a picture of your license plate and send you a fine automatically. My phone can be unlocked with my face. Computer vision is just so banal. We don't even think of it as AI, but it is. Well, it's machine learning. By the way, the reason that this looks so vintage is because it is vintage. Yann LeCun is the guy that invented convolutional neural network. He's now the head of AI at Meta. And this is a GIF I stole from his website that is from 1998 when he came out with something called Linnet 5, which is the neural network that is able to accurately read digits. The reason that is useful is because checks and postcodes all have digits and letters. And so this found a lot of success because it had monetary value. So banks and post offices started using that stuff relatively early, like a couple of decades ago. So a couple of decades ago, things started getting good, but things then quieted down until the 2010s. And then the deep learning revolution happened. And that happened because instead of just being able to recognize handwritten digits, convolutional neural networks became able to recognize pretty much everything. How did that happen? Well, people released millions of, well, over 1 million images online in 2010 with labels. So people labeled cats and dogs, and then they released that for free, and they were like, okay, take my data, and make a bot that can beat humans at image recognition. And so people did that. By 2011, we already had the superhuman performance, by which we mean computer does better than human in this specific benchmark. So, you know, it's a very specific kind of test, but it's still better than a human. And then in 2012, we had a competitor that won by a massive margin compared to the other ones. And what made that competitor so much better was the size. So LeNet 5, that thing that was so useful to banks and post offices, had 60,000 of these knobs and dials in the function that it could change. AlexNet had 60 million. And so people learned the lesson of bigger is better, which is not true. But in this particular case for the images, it did work. And that really spurred the deep learning revolution. And so the point of this historical lesson is what made this machine learning breakthrough that took computer vision from something that was first science fiction, then something that was real but only useful very specifically for banks and post offices, to something that is so casual today you don't even think about it. Well, two things. One, data. Social media, everyone having a phone in their pocket, meant that it was very easy to gather data. And the other thing was compute. So remember the XKCD with the guy standing on linear algebra? Well, graphics processing units that are used for computer graphics and CGI, they're really good at linear algebra. So if you want to do machine learning systems, you can just use GPUs. And GPUs were getting really, really, really accessible because of the video game industry that was really, well, the 3D video game industry that was budding in the mid-2000s. So when you put all these things together, you get a breakthrough. Anyway, so the point is, for the astronomers, we've got images, we can have them looked at by our computers. So, spotting the difference, I think I'll briefly talk about yeah, I think we can do that. So let's put the difference with the universe. Here we've got real pictures from Atlas, an after and a before. This smudgy thing is a galaxy, and here you might see an extra bright little spot. If I subtract this bit from this bit, there it shines. That is a supernova. So that is difference imaging. That's what we do with the whole survey. That's what we do every night, millions and millions and millions of times a night. The problem is difference imaging goes wrong. It goes wrong so many times. It looks nasty very often. Here we've got an observation, a reference, and a nasty difference. There is no difference in the observation. It's just that the difference went wrong. The problem is we've got millions of these differences coming through a night, or potential differences, and only a handful of real objects that we're looking for. If a single person was to look at these and do that by hand, if you didn't take a break, it would take you a year. So we can't do this. 1 year of human work for every night means that we have to automate. And so we use some of these methods like convolutional neural networks, computer vision, to assist us in doing that cleanup. But notice that the CNN isn't early in the chain. See, AI is the last thing you should do, or machine learning is the last thing you should do when everything else has failed. There's many, many ways to do automation. The first thing to do is just basic things. We've got 4 pictures for each patch of sky, right? 4 pictures separated by 15 minutes. If there's a difference in only one of those, it's probably not real. You know, it's probably bonus. But if it's there in 3 or 4 pictures, it probably is real. The other thing you can do is cross-matching known variables to catalogs that we already have. For example, you don't have to rediscover Betelgeuse every night, right? If you know that Betelgeuse is going to vary, you don't have to put it into your stream. And then when you've done all of the obvious, then you give it to a slightly smarter algorithm. Now, the algorithm that we've got is based on LeNet, and it works really decently. It was made by Josh, PhD student at Queen's, or it was revamped by Josh. And what it does is very simple. Well, this is very complicated in the box, but you know, Out the other side comes a very simple number, something between 0 and 1. 0 means it's bogus, 1 means it's real. Everything with a score of 0.2 or above gets passed on. Everything else gets a label of garbage. And that removes most of our garbage. The problem is that left still hundreds of things to eyeball every day. Hundreds of alerts, of order 200 per day. And you have to keep up with it because, you know, every night you get another 200 or 400, depending on whether the moon is bright and whether the sky is like that. Sorry, because I think it's squishy, so my computer's not liking that. It's very hot. I'm gonna be quick. Okay, so we've got hundreds of alerts every night. Not ideal, doable, tractable. People were doing this, but my job when I came in was to help with this because not only is it a lot to look at, but it's boring because most of them are still garbage. There's so much garbage in the difference imaging. It's really hard to do. 85% of those 200 alerts would be garbage, and about half of that would be extragalactic stuff, and half of the rest would be galactic transients, like cataclysmic variables. But automating this is really complex because humans are not that stupid, right? Humans can make good decisions by using data that is varied and data that is incomplete and their expertise. And it's very difficult to automate this process. How do you make a computer use expertise? So the kind of stuff that people would do is look at something like this. There is one data point in the light curve, a whole bunch of non-detections, just a location on the sky, different images, and some contextual information. Is there a galaxy nearby? And with that, people can make decisions within a day. Like with 1 or 2 data points, they can make a good decision. But to do that with a computer, it's a lot harder. So that was my job. I made this thing called the virtual research assistant. Its job is to do eyeballing before people do the eyeballing, to rank and prioritize the alerts. So now you've got 200 alerts, but they don't come as a big medley. They come ranked, and the virtual research assistant tells you, just look at the top 15%, because those are the most sure that there's something good in there. And then everything else is just kind of in limbo. And when there's a new observation the next day, the VRA reassesses, does this look real or does this look bad? Do we put in the garbage? Garbage is the bottom of the list, shows you the top, and then the rest, it reassesses the next day. So how does it do this? Oh, and it works, by the way. This is an old graph, but it works. Here you can see the VRA being 85%, well, 84% of the data that is garbage. And here is the labels for everything. Yeah, it works. So the VRA is just a function, like everything else. It's just a function. It takes in the same kind of data. Don't worry about this slide. It takes in the same kind of data that people look at, and it gives out 2 numbers. There's 2 kinds of models. And it asks the same questions that the humans ask themselves. When the humans look at an alert, they ask themselves, is it real? Is it galactic? If it's not galactic, then it might be extragalactic. If it's real, it's cool. And so the VRA does the same thing, and it ranks things between 0 and 1, not real to real, not galactic to galactic. Blue is the stuff I care about. That's the good, that's the extragalactic stuff. And you can see it populates this nice little corner. And then the next thing, so that's the score that it gives. And so then we have to actually rank the alerts. How do we rank the alerts? We're going to use the newfangled technology of the Pythagoras theorem from 4,000 years ago. It's great. So this is the corner that I care about the most here. And so then I say, well, the closer to that corner, the better it is. And you just calculate the geometric distance. And that's it. The actual machine learning algorithm I use is a thing called gradient boosted random forest. I'm not going to go into the details of what that does. And the special flavor that I use is similar to LightGBM. That is from 2017. It's a paper from 2017. Pythagoras is from 4,000 years ago. And if you mix the two, you get something that works very well and that can take 80 to 85% of the workload off of our humans. So the point is, going back to the initial statement that I made, is that progress in astronomy and science isn't just a partnership between people and different technologies, it's a partnership between people and the right technologies. Those technologies do not have to be new. If the Pythagorean theorem works, just use that. You don't need to add an extra K clustering or whatever ChatGPT told you to do. Okay, and in very quickly in 5 minutes, I'm going to briefly talk about the ChatGPTs of the world. Not just ChatGPT, Gemini, Claude, all of these. So I don't use these. My thing is called a virtual research assistant. So a word that I picked many years ago when I was writing my grant application so that they would give me money, before all of these things were really popular. And so now there's the implication, because it's a virtual assistant, that it is one of those large language models. It is not. It is statistics. It is really understandable. It's not a black box in the same way these things are. And the reason that these things are so tricky is because of something called Sidolian voids. And to explain what Sidolian voids are, I'm going to show you another picture from my phone. So can you see, maybe if you squint, you'll be able to read the words, but can you tell what this is roughly? Oh, airport, exactly. So the reason I took this picture is because I'm blind and I'm lazy. And I was stuck in an airport for 7 hours and I wanted to read the sign from a distance. So I take a picture with my phone and then I zoom in. That's what I usually do if I need to see something from a distance. Except in this case, damn, the generative AI scrambled my words. It looks like wingdings on LSD. And this is the same phone, the same technology that made my stars look so much better when I took my picture of the Milky Way, that made my JPEG look better than the RAW. It's because this type of algorithm is trained to make landscapes, faces, look better. And in landscapes and faces, very few right angles like you have on announcement boards and airports, right? A right angle and a straight line on that scale in a picture, that's a pixel. That's the thing that the algorithm is trying to raise. So this very smart algorithm that works so well for one specific case destroyed the information that I was after in this specific instance. So the Sidolian voids is something that Neil Lawrence came up with. Recommend his book, The Atomic Human. He's a professor at Cambridge, used to work at Sheffield, and then he left straight up. He's a really cool guy, and his book is really balanced and a really interesting history lesson on AI. He's been working in this field for 25, 30 years. He's seen it go through, this is nerd stuff no one cares about, to this is something that everyone on LinkedIn is talking about. And Sidolian voids are a reference to this guy called Lee Sedol, who's the top AlphaGo player in 2016. And AlphaGo is a game a little bit like chess, but there's so many more moves. It's been really tricky for humans to make a bot that can be good at it. But in 2016, the DeepMind people did it. They made a bot that defeated the reigning champion. But AlphaGo only won 5 of the games in the tournament. Lee Sedol won 1. And the reason that Lee Sedol won 1 of those games is because he managed to pull a move that the computer didn't expect. And as soon as that happened, the computer started doing completely random stuff that didn't make sense at all. It behaved really erratically. And that's because learning a function is a little bit like exploring a landscape, exploring a map. So this is a Civilization 5. This is a video game, but the concept is simple. You have a map, you explore it, and if you've not seen this bit of the map, there's a fog of war. Learning a function and learning how your parameters work is a little bit like trying to lift the fog of war to the cities, to the solutions of your problem. The problem is the more you have parameters, the more you have dimensions, the bigger the landscape. Basically, the bigger the number of parameters, the more fog of war you have. In these kinds of gigantic tools, it's more fog of war than it is paths. And if you put an algorithm in this part of the landscape that it's not explored, it starts behaving erratically. That's what Neil calls a Sidolian void. And that's what's happened here. Like, it didn't recognize these were words. these right angles and these shapes, it tried to erase them because it did not know what it was looking at, because it wasn't trained for that. And that's something that's very important for us to keep in mind when we care about the rarest objects in the sky. The stuff I care about is more likely to be in an area that is not going to be explored by the algorithms because it's not generic. It's the weirdest stuff that we can see in the sky. It's very hard to train on something you've never seen before, right? So we need to be careful about the algorithms we use for that. The other problem with generative AI is that it is probabilistic. It's not a problem in and of itself. If you don't know what it is, it doesn't matter. But if you do, I'll tell you the problem is because we don't know the probabilities, because these are black boxes, they don't release the algorithms, they release the weights, but they don't release the data that they're trained on. It's very tricky to actually, and it's very expensive to actually explore these things. Probabilistic just means if you ask the same question twice, you might get different answers, right? So you don't get the same outputs every time. And finally, large language models, they're not trained to be truthful, they're trained to sound human. And the reason for this is because we don't know how to do this. I cannot emphasize this enough. You will see people online and in the newspapers tell you that they found these ways of blah, blah. We do not know how to train things to be truthful. Like, this is an unsolved problem. Large language models are word calculators and they are very impressive. But learning to see the truth means learning a model of the world. You can't do that just by looking at words. So the LLMs can't do that. So these two problems are particular issues if you're a scientist, because it makes your work completely irreproducible. If my work is not reproducible, we might as well be doing astrology. You know what I mean? Like, it's science. It's supposed to be reproducible. So using technology that we do not fully understand in this way, although it sounds cool, it is not workable in practice. And so the thing I'm going to leave us on is this again. Progress in modern astronomy is a partnership between people and new technologies. The right technologies. And just because it's new doesn't mean it's right. A lot of people want to push the new stuff and say, this has been a revolution in this field, therefore it will be a revolution in another. That is not always true. We have to be patient, and we have to be as passionate as we are skeptical with these new technologies, because otherwise we might leave a really poor legacy of data to the scientists of the future. All right, I'm going to stop here.
Well, we're going to have questions and answers.
Let's go.
I'm going to ask Heloise just leave the computer on and connect it to the Zoom meeting. So hopefully she can hear answers online.
If I don't talk, I'm sure that we can turn their thing back on. The reason I wanted to show you this is because one of my colleagues found a supernova here so she found many, but this is one of them. You can see it today. This red dot here, that's a transient. Now, it's not easy to see in the image because there's a galaxy underneath. The reason it looks funky is because there's at least two galaxies merging. But this is a confirmed transient that was found by another telescope, and that was found in NSST at a different date when they were doing their very first look with their ribbon. So yes. So if you want to turn the sound back on.
We'll start off in the room. It will try and bring in people online. The worst case scenario, will you put your question on the chat and I'll read it out. So in the room, have we got any questions? Nothing. Tony Morris.
When you were training the Atlas models, did you use Atlas data?
Yes, absolutely. That's a very good question. This is very common for people to use simulated data, but I wanted to use not only Atlas data, but real data that people had laid eyes on and labeled themselves, because it's very easy to make optimistic data when you're simulating it. And it happens relatively frequently that people make proof of concepts that then fail when they see real data because the training data they had was not realistic enough. So in our case, it was possible because I chose a type of algorithm that is not as data hungry as, for example, neural networks, which means that it can be trained on a few thousand samples. which is easy to get with the 3 months of Bible.
The reason I ask is that in the amateur world, the AI tools have go into the software that we use, but they've been trained on different models which aren't our optical systems and cameras. So sometimes you get really strange artifacts
Yeah.
because it doesn't know how to really manipulate the data against its learned model.
That happens. So there is a way, it works quite well with computer vision if it's doing things with you know,
I took
image
that noise reduction is one of
noise reduction
the
data.
key areas.
Yeah, so yeah, that's tricky. So things can be trained on something, and then there can be something called transfer learning, where you've got something that's trained on a generic data set or something else for another purpose, and you want to repurpose it for something new. And instead of training something from scratch, you use examples from your specific system to train on top of the original training. But obviously, if it's in the software that you buy, they don't know what stuff you've got, there's no way for them to do that. So you're going to have issues. It is something called data drift. That's the technical term. Is the data that is looked at in production is different from the data that is trained on, and then the outcomes can be unpredictable.
Yeah, thanks. So from Atlas imaging the night sky, how long does it take for you to confirm that you found the supernova? And when you do, what happens then? Do you inform the community?
That's a good question. I should have said. So it takes a few hours for the full data process to happen. I think the shortest we've had it is 15 minutes from on Sky to, but like it depends on how much data processing needs to happen. If you've got several telescopes happening all at once, there's a lot more data that needs to be processed in parallel, and so that slows everything down. But a few hours. And then now, because we have fewer alerts to look at, we've got the order of dozens every time instead of hundreds. The biggest latency is people looking at it. So I tell my colleagues to look at it at least every few hours, but no less than every 24 hours. Otherwise, the humans slow the process down. And then for the reporting, we report it to something called the transit name server. So when we see something and we say it's good, and it goes in the good list on our Atlas transit server, it automatically gets added to the transit name server. It gets given a name like 2025, ABI, blah, blah, blah. And that process is not done by the VR. That is why there are still people in the loop that say something is good, something's galactic, blah, blah, blah. Because I do not want a bot, no matter how smart, to be triggering something that informs the community. Because people might trigger telescopes with this information, for example, they might say, oh, and then it can waste resources. So because, you know, the universe is big, but it's not that big. Supernovae are pretty rare, transits are pretty rare. We'll find of order 100, 150 transits a week, right? So maybe a dozen a day. And if we're lucky, a handful that are worth observing. So it is practical to do that reporting by hand. And so that's why that last step is always a human clicking the button. I think that's good.
Thank you.
Just to follow on from that question, Chris Lintott is a big supporter of citizen science.
Yeah.
And your 200 to 400 possibles, you're only looking at 50% of that.
Yeah.
Do you have a program where you've got a group of citizen scientists looking at the rest of that information?
So we don't. So the reason that we don't is twofold. One, the 15% that is most likely good is honestly pretty much the only interesting stuff. If I was giving the other 85% to citizen scientists, I would, like, at the level that our system is working, I know that I would be showing them shit, and it doesn't feel worth their time. And it takes a lot of time to set up a citizen science program and to keep it running, because you need to keep in touch and to take care of your community. We don't really have that kind of like human resources to do this. And the decisions that need to be taken on that 15% that is most likely that where we need that last human like pressing a button. Having a few experts is easier than having loads of citizen scientists. Now that's for ATLAS, but for LSST, I think citizen scientists are going to be definitely a lot more. A bigger army will always be useful, because even though there are many bots that we're making for this, there's just going to be a lot of good stuff, and people will be able to find interesting. So there's already a citizen science program run on Zooniverse. That's the platform that Chris Lembo started. Called, I think, Comet Hunters or something like this. I can't remember the exact name, but there's already a program that's set up that you can sign up for on Zooniverse, as LSST has now started taking pictures to find comets in the data to help people. I know the go-to people rely on citizen scientists quite a bit for some of their real bogus classification. Yeah, there's two different strategies. I feel.
Okay, thanks for that. Great.
Does your machine learning tend to evolve in a linear manner, or does it tend to evolve like a weird evolutionary tree? Some branches will go up the sideline, instead of getting better, they get worse and worse, they make more and more artifacts, and all you can do is kill them off.
Yeah, so I'm not using a genetic algorithm, so it doesn't really work like that. The way that, hang on, I'm gonna find you. It's on my website. So there's a cool GIF I made. So the way that my algorithm works is, so we're building a function, and we're going to start with a really dumb function, a really bad guess. That's basically just the average that we could get. And then we're going to see what the outputs are. And then we're going to make another little function that, corrects for the residuals. We're going to make a little correction function, but it's still going to be bad. And then we're going to make another one, and another one, another one, blah, 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 like 100 times. And it gets better over time. And this is, and you can see it in action here. We've got to wait for it to come back. I is the number of little functions we're adding to our big function, the number of trees, that's a technical term. And you can see how things separate over time. And at the start, you can barely see it. It's a flash, because it happens it gets good within a few, like dozens, like a couple dozens iterations. And then when you get to the later trees, it hobbles around, it's just noise. So it's not that there's branches that are bad, it's that it starts bad because it's a dumb function. And then you just add little bits and little bits and little bits until it gets quite good.
So you're checking for convergence on the data, right?
So I don't so much check for convergence as much as the algorithm descends a gradient. So that gradient is basically the residual. So the residual is, you take the difference. You've got, here is my guess of the bad function. Here is the real answer. That's a delta. A delta is just a slope, right? And so you go down that slope. Exactly how it works is histogram-based gradient boosted decision trees. There is papers and tutorials online, but it's where was I? Where was the pretty picture? Go away. What's this? But it's basically just gradient descent. And so it's exactly where it ends up is hopefully a global minimum, but at least a good local minimum.
Okay. Any questions?
So there's been a lot of noise this past couple of months about the advance in quantum computing, the number of qubits that can actually travel on a chip. So is this going to have an effect in your area?
Nah, I'm sorry. I've got a lot of friends that used to be in quantum computing, and there's some very specific applications that maybe it can do and help with. But definitely not any of that. Yeah.
Peter Lloyd has made a comment, or a question, and he writes, if you jiggle the algorithms until it gives you the answer you're expecting, does that imply that AI can never discover anything unexpected?
Yeah. So it's not quite that bad, but it's pretty much that. So essentially, so that's not completely true. There's specific forms of AI that are a specific form of statistical learning called anomaly detection. So when you're doing statistical learning, you learn a probability distribution. You learn some form of function. In my case, I learned to reproduce it. In the case of anomaly detection, they learn to find things that don't fit. So it's you can use those to find things that don't fit and then make decisions yourself on, well, what could this be? You know, is this useful? Is this just crappy noise? But in the larger context of, for example, language models, the way that they're being advertised, they're solving new problems, etc. They're better than doctors at solving these diagnoses, etc. Usually when they're better and when they do it faster is because they've read the data. In the data that they were trained on, the answers were in there. And so when you're asking them with the question now, they're really good at it. But that's because they've already gotten the answer. It's like a student being able to learn general relativity within 3 years of their undergrad. Are they smarter than Einstein? Don't think so. So no, not really. They can't do. Creativity is a very difficult concept to even assess or quantify. And the way that things are trained, and specifically what they've learned, the fact that they don't have a model of the world, means that their creativity is very much bounded by our own.
Okay. Well, Peter, I think you've hit the nail on the head. I'm looking around, can't see anybody in the room with any questions. There's nothing in the chat. So if you could join in with me and give Heloise Stevance a huge thanks for the salute and astronomy society. Thank you.
Thank you, guys.